Hi everyone, welcome to Atomic Insights. My name is Krish Kabutterwala and I'll be your IB MYP Integrated Sciences tutor. But before we get into learning, it's kind of important to know why I started making these videos in the first place. Well, the assessments are probably going to be the first exams that you take which will impact your future. So it's understandably stressful. The issue is that there's not a lot of material that you can access as a student for the MYP. There's the material that your teachers give you, if they give you any, and then there's a few textbooks that can help. But other than that, I find that the whole process of revising for your exams is harder than it needs to be. So you can treat these videos as bite-sized study guides that can help you revise fast and allow you to give more time to actually practicing your answers, which is what ultimately matters. Anyway, the topic that we're doing today is very short but also very fundamental: matter from chemistry. So let's get started. Today, I want to focus on three things. Firstly, some key tips for the IB that I feel like every student should know going into the assessments. And then we're going to learn about the particulate nature of matter. And then finally, we're going to look at some separation techniques. First thing, and probably the most important thing that you should know when you're writing your answer in the assessments is you have to pay attention to the command term. Obviously, if you've been through MYP, you would know about this, but it's important to understand just how essential understanding what the command term wants from you specifically is, because you will not get all of your marks even if you know all of the technical knowledge, just because you didn't write it the way that the examiner wants you to. So paying attention to the command term tells you what the examiner is expecting from you. So for example, if you see list at the start of a question, like list the types of matters, for example. Then you just want to go ahead and list them, like liquid, solid, gas, right? And if it's state, then you just need to simply state. But if you're given analyze for a question, then you should probably look into a very detailed discussion of that answer, provide multiple perspectives, and really have a good discussion. Tip number two is remembering key and specific terminologies. And what I mean by that is when you're writing your answer, and this is probably important for the answers that are a little wordy. For example, criterion D, or the long response text. So, for example, if you want to talk about bonding, you don't say, you know, atoms come together. You have to say atoms form a covalent bond. And the reason why this is so important is because examiners from the IB really want you to have those specific terminologies in your answers. Literally, it's in the mark scheme, which is like a rubric that they mark you based on. They write, if the student writes covalent bond in this answer, then give them those marks. Otherwise, you don't get the marks. And that's a really easy way to get those marks, because technically you don't even have to be right in your answer. You just need to mention those words which are relating to that. So I feel like that's a really easy way to get those extra marks. Lastly, don't perform under pressure. It's possible to get a 7 even if you don't know a few things. The IB is super lenient. And this is something that my teachers didn't tell me in school, was that even if you say completely flunk a section of the ABCD in the assessments, it's still possible to get a 7. The marking is not that brutal, because let's just say you're not very technically strong, but you're a good writer. So your criterion A goes really bad, and then in the BCD you write really well and you make up for that, you'll get a 7, because the IB is super lenient with that. So don't be under pressure that I got this answer wrong, or I don't know this, then I'm not going to get a good score. That's really not true. All right, so let's get into the actual learning of today's session. First thing I want to talk to you about is all matter is particulate in nature. And what I'm referring to here is, if you see objects around your room right now, the chair, probably the water that you drink, the gas in the gas stove, are all made up of tiny little particles that you can't see with your eyes, but they're there because we check with microscopes. And these form the basis of what we call the particulate uh, matter of theory. Moving on to the first state of matter, we have solid. And in a solid, particles stay in fixed positions in fixed shapes. Solids have a fixed shape and do not flow to fill a container. Particles in a solid have strong intermolecular forces. So, if you can see in the diagram, the particles are very closely knit together in a rigid pattern. And these particles do not move in a solid, right? And I feel like this is pretty self explanatory. So just take a look and make some notes. Then we have liquid. Uh, Particles vibrate in fixed positions in unfixed shapes. Liquids take the shape of the container and have relatively weaker intermolecular forces than solids, but they're stronger than gases. So, while in a solid, the intermolecular forces between those molecules are so strong that they can't even move, they just vibrate in a fixed position. In a liquid, there it's kind of in the between of a solid and a gas, where the intermolecular forces are just enough to keep them together, but it's not enough to stop them from flowing freely, which is why you can see that in a liquid, particles are gonna fill to the shape of a container, right? So in a gas, particles move about and fill the container they're in, and particles have no intermolecular force or bonds and are inherently shapeless. And inherently shapeless just means that they're they're gonna expand to fill whatever container they're in. So all the gas that's, for example, oxygen, hydrogen, whatever is in the air right now, is gonna expand to fill the shape of my room right now. And particles uh, don't have any intermolecular forces them between them at all, which is why they're able to get so far apart from each other, right? This is a graph that I think is pretty helpful on understanding how these states flow into each other. And what you want to focus on, and what I've been asked before in my exam, is why, even when you're applying heat, or you're applying a lot of time in this case, to the solid liquid mixture, but it's still not changing temperature. So why is that? Why is it not immediately just becoming a solid to a liquid to a gas? Why is that happening? So like I said, these states of matters are really defined by the intermolecular forces between them, and these forces are really really strong. And while you're applying the temperature, you're making them weaker gradually. So when at the point when you're making it from a solid to a liquid, it's not to a point where they can flow freely like a liquid, but it's also not a solid, right? Because it has more energy than a solid. So we can say that it's in a solid liquid mixture type of state, and the temperature in that state doesn't really go up because all of the energy is focused on releasing these forces. And same goes for the liquid gas mixture. Now, one of the most important organizational structures that I think you're going to find in a lab is differentiating between elements, compounds, mixtures, etc. Because you have a lot of those in a lab. For example, you have a pure solid element, which is like gold. If you have a block of gold, it's just the atoms of gold in that block. Or if you have a pure substance, an ionic compound, for example, salt, NaCl, which is an ionic compound, and it's just salt in that. It's made up of Na and Cl, but it's still purely only that substance, right? And then we have gas mixtures, which is probably what you're breathing in right now. And you have a pure gas, which is oxygen, or we can say nitrous oxide, which is what they give you at the dentist's office. And a mixture can really be anything in any context. It's like an element plus a compound. It can be different variations of things. A mixture is basically anything that doesn't fall into substance or an element. Yeah. Now we're going to talk a little about the separation techniques. And the first one we're going to be talking about is boiling. Boiling separates the liquids from the dissolved solids. It relies on boiling point, and it's very common in purification. So let's just say you have like a lot of chunks of tiny little chunks of wood, and you also have water, which are soaked in water, right? So you want to separate the water from the chunks of wood, but you don't know how to do that. So what you can do is boil that water, and the water is slowly going to evaporate and move away, leaving those little chunks of wood behind, right? And because these chunks of wood aren't going to evaporate as easily as water might, uh, the wooden chunks are left in the bowl while all the water drains out, and you have effectively what you have is two different solutions. Next up is filtration. It separates insoluble solids from liquids, uses a porous barrier to trap solid particles, and liquid passes through while solids are retained. I would say filtration is one of the most used techniques for separation that I've seen in a chemistry lab. All of the time when you have something, you need to put it in a solution or a buffer of to do an experiment. And when a product forms, you're gonna probably need to filter that out because the product itself is solid, but it's in this liquid mixture form that also contains water. So how do you separate those two things, right? So what you can do is use a filter paper or a sieve if the particle is big enough, and you can put the solution through that, and everything uh, that is important that you need is gonna get stuck on the filter paper or sieve, and everything that's liquidy is gonna fall to the container at the bottom. Then you have magnetic separation, and it separates magnetic materials from non-magnetic materials and uses a magnet to attract magnetic substances. It's commonly used in recycling and mining. So for example, if you let's just say you're mining, right? And what you want to do is you want to separate all of the useful iron ore from all the unuseful bits of rock that you picked up on the way. So what you can do is you can just lay them all out, and you can run a magnet on top of that mixture. And what's probably going to happen is that everything that's useful, all of the iron bits are going to jump on top of the magnet because it's magnetically attracted to it. Meanwhile, the bits of stone probably not going to do that because they don't share the same magnetic properties. So you can say it's very commonly used because again, it's just very cheap to do, and it's very easy also. Lastly, we have distillation. So in distillation, you want to separate liquids based on different boiling points, and it heats the mixture to vaporize the component with a lower boiling point. Vapor is cooled and condensed back into liquid form. So when you have the impure liquid and you have two liquids with differences in boiling point between them, and you're boiling them, the one that's going to have a lower boiling point is going to get boiled first, right? It's going to evaporate up and through the cold water, or what you call a distillation machine, right? It's gonna cool that gaseous gas down, and it's gonna make a distilled liquid. So the distilled liquid is gonna be the substance which has the lower boiling point, and the distillator works on the concept of cold water to cool the liquid down. So that's it for the first part of the series. Hope you found something that is going to make your revision a lot more easier. Thank you for watching. Like and subscribe, and please let me know what you think in the comments.